Cool. Let's get started, huh? I sure could give you my
We're still want to go to coffee.
Maybe it's just right here.
Good to see you.
I can never see you. So it's my great pleasure to welcome everyone to the final presentations of the Engineers for Exploration Summer Program. We had 15, 20 some people participating in different ways. Some of them funded by the National Science Foundation, the Science Foundation for funding that. Others in different ways. It was great. However you were here, it was awesome to have you here. I hope you had a good time. Did a little research, learned what it's like to be a graduate student, maybe about that kind of stuff. It was definitely a pleasure to have you here. It was really, really good. Yeah, we really enjoyed it. You're, kind of graduating into a set of alums that have been National Geographic Explorers and grad school PhDs. We just heard from one that was starting a postdoc at Cornell, doing the first one. Anyway, you're graduating into some really great people, so they'll continue on to do cool things. I'm sure you will. Been in touch, for sure. So yeah, without further ado, we'll go through the presentations. What we're going to do is we're going to just have each of the groups come up and talk a little bit about what they did over the summer. And we're free to take questions whenever. Maybe drop line, you can just type them in and we'll ask them. Here, you can just raise your hand. Okay. All right, great. So first team is FishSense.
So thank you, Ryan, for introduction. We are FishSense, and we're interested in kind of understanding the health of our oceans through ecology and through fish population health. And the way that we understand fish population health is through lake fisheries. We understand how the lengths of fish are distributed kind of over species. We can understand how that changes over time. The way that we can do that is by taking pictures of it. This kind of gives us the apparent size of the fish of the image, but we can add something like the laser sitting on top of this camera to be able to add additional depth to that image to be able to understand the distance our fish is from that. And the way we can do that is through perspective. So we can observe that this laser that hits this building is closer than the laser that hits this building, or this laser. And that this laser vanishes towards the vanishing point the further away the object that you're trying to track is. So,
with the help of this information, we're able to estimate the length of the fish. But for that, we have to know the position of the laser, the position of the head, and the position of the tail in the image. Now imagine dragging your cursor all the way over to the laser, the head, and the tail, clicking to determine its position. Now imagine doing that again, and again. You see, after field deployment, we have tens of thousands of images. And in all of these images, we need to label the laser, the head, and the tail. This is an immense amount of data and would require months of work if done manually. Therefore, we've developed software to more efficiently handle this data.
So the bulk of our work this summer was to define this kind of processing pipeline in order to go from fish images to fish lengths. So the way it currently works is before any processing has to be done, these blocks up here are basically things that need to be done before any processing, particularly calibration, to determine parameters about the camera lens and the laser's exact relationship with the camera, which we need to data sets. So in addition to that, we currently have it so that laser dots and head fork points have to be manually labeled, which takes time. So we'll go into how we automate that later. But the process is essentially we do some pre-processing on all the fish images, and if there's a fish in a laser in the image gets undistorted. We calculate the distance to the laser because we know where the laser is with the camera, and we use our head tail points and the laser to calculate fish length. And we'll go into the parts of this that we automated this summer.
For the pre-processing, when we take a picture, there's a lot of image processing and compression going on under the hood of the camera, and oftentimes we don't understand exactly what those processes are. They may result in sources of error. Therefore, I've written software this summer to allow us to control how the raw sensor data is processed into a visually pleasing image. This also helps with laser detection. For laser detection, we've tried various approaches this summer, from signal processing to edge detection to interest point detection and to Gaussian curve fitting. But the approach that we've been having the most success with is a machine learning technique.
So what do we mean by machine learning here? Basically, we took this artificial neural network, a really lightweight model, and we put in 20 by 20 tiles, like 20 by 20 pixel tiles into this network. And we told it whether or not there was a laser within that tile. So after seeing thousands of these tiles and training for hours, we received around 98% accuracy in the pool, which basically means that if there was a laser in the image, we would find it 98% of the time. We noticed that there was a drop in accuracy though, as you went to ocean data. And this makes sense because oceans are here at pools. But what we did also do was that we biased our model towards false negatives. So what does that mean? It basically just means that if there was a laser in the image, in the ocean, we would find it 98% of the time. But if there wasn't a laser in the image, or if there was a laser, but we didn't find it, there might not have been a laser in the image. And that's sorry. So we would bias it towards false negatives. So what that basically means is just that if the model did detect the laser in the image, 98% of the time what it detected was the laser. But if it didn't predict anything, the laser might have still been in the image. And that's okay for our physics model just because our length detection requires that we find an accurate laser point. But because we take multiple images of each fish, if we don't find the laser, that's okay, because we have multiple images, we can try again.
One other thing that we focused on this summer was automating the laser calibration procedure. So the way that we kind of did this before the summer was we would basically shine the laser on any surface and manually measure the distance between the laser and the camera, and that involved deploying a measuring tape over the length of an entire pool and recording the distance at which the camera took the picture. As you can imagine, that was really tedious. So what we've done is you put the laser on a checkerboard. The advantage of using a checkerboard is there exists algorithms that you can use to detect where the checkerboard corners are in relation to the camera. That's really useful because we can use those points to define a plane. Once we have a plane, we can see where the laser beam intersects that plane to get a more accurate laser elevation. So so now we can just take pictures of a checkerboard at completely arbitrary distances and use those images to calibrate the laser. So we no longer have to go through that tedious measurement procedure.
So far we've been operating under the assumption that the images that we get are pretty accurate portrayals of kind of what's in front of us, but it's a problem if they aren't. So on the top right, we have something called a reflective optic, and top left is something called a flatboard, and those are just kind of the lenses we put in front of the camera for underwater housing purposes. So this image corresponds to the flatboard, what the flatboard takes, and that corresponds to what a reflective optic takes. So far, our system uses a reflective optic because it will produce images that are undistorted. You can see the planes are pretty flat, it's pretty accurate to what's in front of us. However, if we want something for citizen scientists to use, the reflective optic is pretty expensive, so it becomes inaccessible for citizen scientists. So instead, what we want to do is drop the reflective optic and just use a flatboard. However, you can do some pretty intense curvature on the top of the checkerboard, the top of the stairs, and that obviously causes issues for artificial and depth measurements. So what we want to do is be able to model these distortions so that we can understand what causes it and how to possibly prevent it. So the distortion that you saw is caused by something called reflection. So a light ray is traveling through surfaces and it's going to change direction based on the density of that medium. So for our purposes, the light ray is coming from the fish, traveling through the water, it hits the acrylic, which is kind of a flat port material, it will change direction, then hits the air again, it'll change direction, and then it'll go into the camera. And that is something that we can mathematically model, and something that we did on the right over here. So that's essentially just the same idea of a bunch of light rays coming in, we can trace their points back and see how they refract, and we'll show up in the camera. We did that for a lot of different parameters, so different thicknesses of the acrylic, thicknesses of the air, distances of the fish, and this is all dependent on stuff like salinity of the water, temperature, wavelength, and these are all sorts of simulations that we ran through so that we could see how our images would be stored. And two of our most consequential, tests that we ran are shown up here. So we can see here, as depth increases, we have a varying percent error of our length estimations, or of our simulated length estimations and depth estimations. So we can see that we would, if we had used a flat port, we could pretty severely underestimate the length, and as we go further out, we could pretty significantly overestimate the length. And the same can be said about if an image gets stretched out. Well, an image does get stretched out for this distortion, so you can also see that depending on where you are in the image, so like if your fish is on the edges of the image, your link could get stretched out and position will change relative to where it actually should be, which will affect the image definitions. So going forward, we want to take these mathematical models and see how we can apply possible corrections and account for this, since it's a predictable behavior in future renditions of FishSense.
I'd like to thank our collaborators, I'd like to thank our advisors who helped us along the way, and I'd like to thank the team who's put in a lot of hard work this summer. We've had field deployments this summer that have seen some very last minute work to make those happen. We submitted a paper for publication, and through all this, my team has been ensure that we're successful. So again, I'd like to thank my team for all of their hard work this summer, and open up the floor for questions.
I guess I'm sort of the general audience here. So have you experimented from a scaling perspective? Did you experiment with dual lasers with a known distance between the two lasers? This way that distance is maintained no matter where the target is? Is that what one of them? And then the second question is that did you also experiment with blue-green lasers as well as that?
So let's start with the dual lasers. So our collaborators in SIO have previously used that in their work, and what they kind of come across is that these are not manufactured to super tight tolerances. So the axes of the housing and the axes of the lasers may not match up, making it kind of really hard to keep these lasers, like find first off two lasers that are compatible to be put in parallel, and then slight jarring of it causes them to lose calibration, which leads to error. So our hope with this system is that it's more accessible to citizen scientists, because the calibration for this is just kind of less sensitive. While we didn't present it here, we do have a method of like recalibrating in the field, and one of the things that we were able to kind of work through is how do you do these post calibrations to correct through these errors. So our system is robust in that way. And then as far as the red-blue lasers go, green and blue lasers go, we initially developed the system with a green laser and found that the fish, that it impacted fish behavior. So we did some kind of like reading and talking to our collaborators about that. They had similar like experiences that we were able to validate that a lot of the fish that we were focused on can't really perceive red, but have much better perceptions of red. Yes.
So the fish can't perceive it. Is there a significant loss of range in red due to attenuation? Or?
Yes.
So when we did our full test, we found that the red lights kind of attenuated 46 meters, and like 25 yards how far the green lights went. The effective range we're trying to get is around 46 meters.
So within the range that we're interested in, the red laser is sufficient.
And part of the like citizen science aspect of it is like sort of virtual spearfishing.
And so you can take a picture of it and then you can come back and say, I caught this massive group or right. Two lasers, I think part of that is just the simplicity of the system. So I think the two lasers probably work better. I mean, worst case, you could just throw one of them away and it would still work with your system, right?
Yeah, correct. Yeah.
So it's just a little cheaper.
You're seeing comparable results actually.
Yeah, they're showing that it works pretty well.
And the nice thing
Do you
about
have the camera?
I don't.
Okay. They're all being deployed.
Yeah, they're all for
Okay. Yeah, they're all out right now. It's just a little mount that they
I have
laser on it.
this. It's hard to see in this picture, but
You can also correct me if I'm wrong.
Yeah, so a lot of divers already have that camera. Yeah, so just maybe we can give you this extra laser and a mount. Cost, I don't know, 10 cents to print.
yeah, and the laser mapping bugs. So integrating, so we can integrate already existing pipelines. The other thing is that this design is open source. So anyone in the world can go build one of these cameras without us being involved and contribute to kind of the system science aspect of this.
Great, can we move on?
Cool. Yeah, we'll move
Fantastic work.
on. Sorry. Cool. So, I'd like now to introduce radio tracking usage.
Hi everyone, we're here to talk about the radio color tracking project.
Alright, so Nick is not here today. You might hear from him later on during the presentation. But my name is Sunny Ket.
I'm Nina. So I'll talk a little bit about the motivation for this project. So right now, zoologists and ecologists are interested in tracking animal movements, both to understand more about these animals and to observe how their habits change depending on environmental factors. And right now, the tracking is done by connecting a radio transmitter to the animal. In our case, lizards and snakes. You can see one in this image. And then going into the field with a handheld antenna and listening for pings and then following them until they're close enough to tag the location. So our project aims to make this tracking easier, more efficient, and less invasive. And we have a few methods for doing this.
Right. So in the past, radio tracking has used drones to kind of reduce this manual and invasive tracking work. So basically, we attach a receiver to the drone and flew it over the search area, and we try to pick up things from the trackers on the animals within their search area. But due to changing requirements and methods, we are also exploring some other strategies of optimizing this method. So two strategies we are exploring this summer is using a radio tower and also a robotic dog. Both of these we'll talk about in just a little bit.
So this summer, and I'm sorry, our font must have changed like last minute, but this summer there were 3 of us working on this project, all on different aspects of the project. So Anika worked on the tower electronics, Nick worked on communications, and I did some work with hardware for the robotic dog and for developing the PCB protection at all.
Alright, sorry about the font again, but so let's talk about the tower electronics. So why do we need the towers? Our goal is to track common polyp lizards in Arkansas, and we want to achieve this with a high frequency. So pretty much we want to get localization results about every 10 minutes or so. This is not really possible with that drone solution we showed before because it takes a lot of time to charge up a drone, fly it, bring it down, and maintain it, and it's really just not possible within 10 minutes. So we have explored solutions to place a network of drones out within the search area and pick up our things from the trackers with a much higher frequency. And one of the main aspects we have considered with this tower electronic setup is power conservation. This is because all of our towers are powered with an isolated power supply, And our goal is to also maintain a decent lifespan for all of these towers in the wild. So let's talk about the tower lifespan. If we just put our towers into the field and run them all the time, we would have only about 2 days of lifespan. This is not really that good because a lot of the locations that our towers are aimed to be placed in are pretty remote, and all of our equipment will have to be hiked in there, and 2 days is not great when we expect the lifespan to be at least 2 weeks. So without any sweep timer or power conservation, 2 days will be maximum if we place the towers as well. So we need sweep conservation. If we add sweep conservation to it, we can conserve energy, which will increase the lifespan for towers to 14 days, which is much better and also meets our 2-week requirement. Right, so what you see here is pretty much a diagram of how the towers are set up. What you see is that we have a battery, which is our isolated power supply, and we have an onboard computer and a sweep timer. So the onboard computer is responsible for collecting data, processing it, and sending it back to the head node. And the sweep timer pretty much controls all the power to the setup. Since the onboard computer is much more power hungry than the sweep timer, we want to shut off the onboard computer whenever we are not collecting data or transmitting it. So whenever the onboard computer feels like its job is done, it sends a message via the optical isolation cable to the sweep timer. And the sweep timer pretty much just controls the switch, cuts off the power to the setup, and continues that until it decides that we need to collect more data, and it turns on the setup again. So this is a strategy we've explored to preserve energy. This summer we've explored, my work has pretty much involved with integrating the optical isolation cable and the sweep timer within this tower setup. So the optical isolation cable is pretty much a bilateral communication line between the sweep timer and the onboard, and it allows us to send messages and talk between the two processors. And the sweep timer, again, as I mentioned, controls the switch and is also responsible for controlling power to the setup. So I've worked with integrating the optical isolation cable as well as the firmware for the sweep timer, and I've worked on ensuring that whatever message is being sent from the onboard computer is being heard by the sweep timer and is being recognized and correctly put in memory. Now let's hear a little bit from Nick about the communication side of the tower.
So how do we use long-range transmitters, more commonly known as LoRa transmitters? We know that with our current tower system, we need to be able to transmit from long distances while also creating bilateral communication, which means that we're able to talk to and from the same node to other nodes. Being able to receive and transmit multiple messages was very important to us in this process in developing the LoRa system. Not only does information need to be transferred bilaterally, but we also need to be able to send information from long distances. This will help in the later process when developing the LoRaWAN gateway, which is a future implementation we plan on doing. Now, if you look over to the top left of the slide, you can see our collared lizard transmitting at step 1, a signal to our transmitter at step 2, which is the Ryler 896, which we decided on for this project, which then goes into step 3 at the top right, where we see the range from 10 to 15 kilometers being covered to transmit the information from step 2 to step 3, indicating that these nodes are able to receive and deliver messages to one another, creating a network of nodes. This also means that each tower within our network of nodes consists of one of these transmitters. Now you may ask, with all this in mind, what do you hear over there? We needed a way to not only identify, but also act accordingly when trying to figure out functionality of how these nodes will work with one another. Within each tower system, we are able to have bilateral communication, which allows us to not only transmit data, but also listen independently as well. Now, as you can see from this example, we have the collared lizard kind of doing the same thing as before, but with now we get a more real sense of what was developed over the summer and the information being shared between the two towers. So instead of just having both towers listening, we have one tower listening, as you can see at the very bottom, where it's saying, hey, the lizard's over here, and then sending that message to the tower above it, where that tower is then being like, hey, it's over here, it was spotted by this tower. And then that information would be then transmitted to our LoRaWAN gateway, where we're able to actually interface with the data being received. It's to be preferenced that there will be multiple towers, and each of these towers have multiple different functions to them.
All right, so thank you to Nick for talking about the communication side. This summer, we also worked in collaboration with San Diego Safari Park and the University of Southern California, which owns this quadruped robot. And one of the ideas for radio color tracking is to mount all of our electronics and this antenna you see here onto this robot. Then they're working to install a solar panel onto the bot and then have it go out and just autonomously track rattlesnakes at a safari park. So we had our preliminary test of this robot with our electronics over the summer. And one of my projects was designing a payload box to be attached to this bot. And you can see our final design here. We went through a lot of design changes and iterations to get to this point, but here, this contains all of our current electronics, and then you can see, of course, the antenna mounted on top. And on the next slide, we'll see a video of this dog walking. So the idea is, of course, this creature will go out into the field, listen for pings, follow them, and send information back to a base camp. We ran into some issues. For one, I don't know if people saw, but in this video, the antenna was wiggling a lot, so we're working on developing a new antenna strategy. There were also some electronics connection issues. So after this deployment, I worked on developing a PCB that would solve some of these problems. So here is an image of the actual physical PCB that ended up making for that. The goal of this is to simplify a lot of the connections and clear up the issues that we had. So ideally, when this is implemented, it will decrease the amount of electronics, meaning we can have a smaller box, and it should also help with transmitting information back to our base. Hopefully, this will be put into all three of the radio tracking project. So if there are more drone iterations, it should be implemented. And then, of course, into any future work that the towers work on.
Yeah, so on this slide, you can kind of see a quick review of all the stuff we've worked on this summer. You can see a little bit about next communication word. I work with the tower electronics and this with PCB hardware. And for the future, we hope to integrate all of these individual works into one cohesive unit, hopefully the tower setup, which we plan to deploy and test.
Thank you all for listening, and many thanks to our advisors and to our collaborators. We'd love to answer any questions you guys
Are we able to just jump in?
Yeah, go ahead.
Oh yeah. Ela, could you tell us more about what the custom PCB does in the system?
Yeah, for sure. So we, for the electronics that we brought to the zoo, we had inserted a USB splitter. So right now we have a UI board that connects to an up core. And the idea of this was to get rid of this UI board that we had previously programmed, had previously designed, and then to add in a lot of the connections from the up core, which is like the brain of the device. So the up core has an 100-pin connector, and that connector's like other part will be soldered onto this chunk of the PCB. So right now, the 100-pin connector has like all of these logic outputs, none of which are really being used. And by creating this board, we're allowing all of those to be connected, and then we have breakouts for a lot of the important things from this connector. So we'll be able to use a lot more directly from this board rather than exporting things out to a UI board and then also to a USB splitter and splitting everything up into more like manual. This should be like moving more of a logic to this board.
Thanks.
What frequency band are you transmitting in?
I think 900.
So which band? So there's several frequency bands that are in use for this. The tracking is actually done over VHF at 150 megahertz, and then all of our telemetry is being planned for 900 megahertz.
Gotcha. So 10 to 15 kilometers is a pretty great range. Or like 915, I think usually what we work with, and that's pretty, you'd have to, put a lot of power into it to get that kind of range. So 50 makes a lot more sense.
So the quadruped robot that you were using, is that, I'm kind of curious, what was its task prior to this project? And is it visual or LiDAR or SLAM enabled? Is it kind of positioning system or collision avoidance on board? Or how were you able to task it to follow the signal, right? I mean, if that's not what it was necessarily intended for, I mean, there's got to be some interesting bit of engineering there to get it to actually move towards a signal rather than move towards some pre-programmed or assigned location.
Yeah. So right now, that robot is owned by a University of Southern California lab, and it is doing pretty different stuff. I think their ultimate goal, like their main goal for their lab, is to have it like hit the ground and then tell them like about the rock in the ground from like the way its leg reacts. So it's pretty different than this. And we are on we're in a pretty early phase of the project with this robot. So it hasn't been like fully set up to track the things yet, but the robot has, I think, GPS on board, and it's pretty like well developed. We got to see it doing some testing on like steeper hills or rough terrain. It's able to react like well to its surroundings. It has this thing where if it trips, it like flips over and then walks on its back. It's able to like run into things and then avoid them a little bit. And I think moving forward, we're gonna have to work a little more to like actually get the pings and the robot like to obviously combine together to actually track. But I think the goal is that, we'll find a way to get a lot of our electronics and their electronics kind of implemented together. Because there's a lot of space in this robot, and I think it's very possible to like have a lot of the robots and turtle watching people to power.
Yeah, there's so many interesting challenges with something like that, right? I mean, I suppose if you know the topography of its range, then you can preload that, and then it could know to avoid, it could take a least cost path approach, which takes into consideration known obstacles, and then it would have its own collision avoidance, but it'd be interesting to see how it gets to where that signal is, which is challenging, and it's all these different aspects of a project like that.
Interesting. And then there's also the idea of doing a more like more of like the tower sort of approach where it just kind of does triangulation. So I think most likely that's what'll happen first. There'll be a pre-programmed route and then it'll stop, take readings, and then go a certain amount, take readings, and then from that use triangulation to figure out.
Yeah, Ian, I don't know if you have anything to add to that, to your sort of your idea.
Were you just talking to me, Ryan?
Yeah,
Yeah, certainly. So, you know, as you said, this is a nascent project, and in many ways, we're going through a series of sort of feasibility tests to figure out what is possible with the different technologies. At the very core of that is you know, the robot being able to get around to the place they have to get around, and Ela kind of addressed that, I think, pretty well. There's a sort of slew of potential strategies that we might use that have a lot to do with the way that E4E's radio tracking system might integrate with the robot, especially at that height, which is very different than where the drones had that system. And so the two possibilities you already kind of underscored, one is you have the robots following these fire roads and along sort of known transects, and hopefully getting close enough to the snakes that you can still build up some data from E4E's system. And then more aspirationally, someday is the idea the robot actually sort of pursues the signal more directly and kind of follows it. And one of the things that we found with USE's work so far, and you know, Ela's right, they do the stuff where they test the ground, but they also do a lot of stuff based on generating novel gates to get through unusual terrain. So potentially they might be able to do that for the kinds of terrain we're dealing with, and just having to walk through really heavy brush was impressive. So but when it comes to full-on autonomy, as the question asker addressed, you know, you really have to get some more local situational awareness, even with really high accuracy GPS. And so we are actually sort of seeking an additional partner on the project who can bring that expertise, and we think we might know someone who's at UCSD who fits, but we haven't asked them yet. So anyhow, there's a lot of different pieces that are coming to play, and this is just one of the things we think we might do with the robot. So you know, we'll see how it all goes. Does that help provide some context?
Yep. Yeah. He's from San Diego Zoo, so he's one of my collaborators, mentors. Okay, move on. Thank you very much. Great work.
Hi, I'm Derek. I'm going to be talking about the WOE project. We're working with the Scripps Institute of Oceanography, and I'm at the Jaffe Lab for Underwater Institute. I'm a CS leader. So I'm going to talk about like the problems that WOE is trying to address. One of the biggest things that we're trying to solve is explain how plankton migration happens. So if you didn't know, plankton migration is one of the largest migrations that we have on this planet. Plankton go up and down in the ocean column, and as they do, they can form these dense patches in the ocean, and we see that as red tides, as shown in this picture. And we don't have a great understanding of how they happen, and we can't really predict when they will happen, but when they do, they look amazing, as you can see here. Another thing we're trying to solve is oil spill propagation. So when a tanker drops oil into the sea, we want to be able to understand where that oil is going and better aid in cleanup efforts.
And the final thing is climate change. So climate change is a big buzzword in this kind of research, but as currents regulate our climate by transporting warm water from the equator to the poles and cold water from the poles to the equator. And as our climate warms, the poles start melting more and the equator gets hotter. And that actually increases our current. And there's been a lot of studies to show that ocean current actually has a direct correlation to the warming of our planet. So let's talk a little bit about what VOLT stands for. So VOLT stands for Vehicle for Observing the Gravity of Transport. And basically what that means is it's a fancy way of saying that the VOLT stays in a position in the water column and it is transported with the ocean currents. And as it's transported, you can track it, as shown here in this video, and get a good understanding of how our currents are moving. So if you see here, we have, this is from an older deployment, we can see the bolts moving through the ocean current together. And we can see how the ocean current actually affects their position as we keep roughly the same depth. So let's talk a little bit about where this data came from. So this data was from the MAUE project. This was the predecessor to VOLT. It was from 2015. It was made out of syntactic foam. We had a limited sensor suite. One of the biggest problems is our localization was done by listening to pings, and the linear actuator on board was noisy, which caused us to not be able to accurately understand their position in the water. And we had to do a lot of work to figure out our position. And finally, once it came up to the surface, we could use GPS and send our location via satellite radio to get picked up by the boat. So in VOLT, it's going to be a lot bigger. It's an aluminum housing, and we have a full connectivity temperature depth sensor on board. So that way we can get a better understanding of the water column that we're traversing through. We have a much more powerful linear actuator, so we won't have to run it for as long, and it should be a lot quieter, so that we can localize ourselves. We have a 900 megahertz radio, so we can talk directly to the boat once we come up to the surface with GPS. And finally, we have an acoustic transducer on board. So in the MAUE project, we just listened for pings, but in the VOLT project, we can actually talk back to the pingers, and I'm going to talk a little bit more about our localization system. So a lot of my summer has been spent working on how to position things underwater. So GPS doesn't work underwater. The GPS waves get refracted and you can't really understand your position. But what we do is we have pingers at the surface which know their GPS location, and they send out pings. So basically what was done in the MAUE project is we use the time difference to arrive at localization algorithm. So in this algorithm, pinger 1 will send out a ping with its GPS location and the time that it was sent. And the VOLT can look at the time that it was sent and the GPS location and figure out that it's somewhere on that red line. And then pinger 2 does the same thing, and we know that now it's between those 2 points where the line intersect. And with the third pinger, we can actually figure out that the VOLT's exactly at that position. And this was this algorithm doesn't require the VOLT to send anything. We can the pingers have to be synced together, which is one of the biggest challenges with this algorithm. But this allows our VOLT to save a lot of power and we have a lot less pings. But now that we can actually transmit with our VOLTs, we can employ the two-way ranging localization algorithm. So in this algorithm, pinger 1 will send out a ping, and then the VOLT will actually respond. And once the VOLT responds, we can look at the times and figure out that the VOLT is somewhere on that server. Then we do the same thing for pinger 2. And we now know that it's between that point and the point off the screen. And finally, with pinger 3, we employ the same algorithm, and we know that the VOLT is exactly at that location. So this solution doesn't require any time sync between the three fingers, but it does allow us to figure out the bolt location, albeit with more pins that have to be sent from the bolt. So what we're planning on employing is a hybrid solution. So in this hybrid solution, we actually combine the time difference of arrival algorithm and the two-way ranging algorithm. And so if you think about it in this diagram, we can probably figure out the position of the leftmost and the middle bolts with the time difference of arrivals algorithm. And we can probably figure out that it's between 2 points, that the third bolt on the left is between those 2 points. But the bolt on the right probably can't communicate with finger number 1 because it's too far. And in this case, we can actually use two-way ranging between one bolt and another bolt that knows its location and figure out that it's somewhere on that line. And once we do, we can actually figure out the bolt's position. And this hybrid approach lets us position ourselves in a variety of scenarios. So we can position ourselves to other bolts, we can position ourselves to other fingers, or any combination of the two. So a lot of the work relies on having an accurate time. So you know exactly when you're setting your ping and exactly when you're setting your ping, and you need extremely accurate clocks. So we are employing time schedule code, and a lot of my summer has been spent experimentally calculating the timing of transmission and reception of the data. So 2 days ago we had an ocean test where a lot of my summer was spent deploying these, so getting them in a state where we can actually put them into the ocean and test out how well they range. I want to thank all my collaborators, Jules, Kurt, Devin, Mike, Ryan, Andrew in the back. Yeah, and if you want to contact me, let me know. If you have any questions.
Yep, very clever. I was curious, is the linear actuator part of the buoyancy control system on board? So and then there's probably a pressure transducer to communicate depth, and then it goes down to a certain depth and then holds that depth.
The CTD, for instance.
Yeah, as well. Yeah, this is really good.
Yeah. Tracking the depth or pressure is like the simplest approach. And so that's what the AUVs did. So the new one, the CTD, you can go, in theory, you can get the holy grail of density tracking, where you're tracking instead of sticking to just 100 meters, you can track a specific node density gradient and try to follow that as that shifts. That's where the internal waves will propagate as upon that density shift. But as you can imagine, that's a lot less stable.
Yeah.
Design, depth is pretty straightforward.
Yeah, well, no, that's actually very clever. I hadn't thought about that because that density layer may change depth or altitude, depending on how you measure it, but it's tracking it at that density. Yeah, it's really.
How many of these are you thinking about doing at a time?
Yeah, hope is 15.
15?
So,
They'll probably be pretty close then. They're all going to just sort of track some of the unknown.
and that was why we had, Derek with us working on the hybrid localization technique, right? Is that previously if you put out your 5 surface pingers, they're just more in place.
Yeah.
Sometimes you get lucky and your swarm stays
We go
there
right
for
through there.
an hour. Other times,
So you go the opposite way.
yeah, like 2 of them split in half and run out at a couple knots, and you have like 30 minutes of data.
Yeah. But the ones underneath themselves could just sort of do their own localization, right? Yeah. They're programmed to sort of track the same thing. They should, in theory-ish, say the same thing.
That's the thought, yeah, that they can kind of track that information as it spreads out away from the known position result.
What does the propagation of error look like with the hybrid solution?
The propagation of error. Yeah, so you probably will have some accumulated error. they can probably employ some algorithms, like there's been a lot of work here. Like just dead reckoning and stuff like that. But, like just trying to figure out your position from like accumulated error and like accounting for it. But I'm hoping that at some point we'll be able to talk to a service finger and figure out a bit of node. Great. Next up is Smartfin.
Hi everyone, so we're Team Smartfin. This summer we have been working on a new version of the previous Smartfin model, which is a type of sensor that is implanted into a surfboard fin that's able to track different types of ocean data. My name is Josephine Dominguez.
I'm Elizabeth.
I'm Emily Thorpe.
And I'm Gordon Reichart.
Sorry, there's some lag going on here. Okay, so there are multiple key ocean metrics that are typically tracked by buoys, but because of that, it's really hard to keep these up to date as buoys are unreliable and pretty difficult to fix. Within San Diego County alone, there's about 15 buoys, and a lot of times many of these aren't in operation. These are public buoys. There's more private ones, but because they're really hard to fix and keep up to date, as I was saying. But imagine if a crazy lineup of surfers like this could be turned into buoys. And that's what Smartfin is doing. It's utilizing citizen scientists and then taking these surfers and allowing us to collect ocean data from all of these surfers. So previous Smartfin data looks a little bit like this. This is our Smartfin 2.0. And so this is along the coast of San Diego County also. And as you can see, there are a ton of data points here. So our goal for this summer is to continue developing the Smartfin so that we can get more data like this. So this is a little bit about our current system that we've been working on this summer. We changed the main control device. It's called a system on a module, specifically the tracker system on a module. And so we were trying to figure out how to reintegrate all of our sensors and peripherals into a new controller. The reason we're doing this is because we've transitioned to 4G cellular data. And that's important because we were previously on 2G and 3G, which is now obsolete. In terms of the sensors, a lot of that has stayed the same. So we still have a wet-dry sensor, a motion sensor, and a temperature sensor. And that motion sensor is for wave height. And then additionally, we also now have GPS on board. So a lot of our work with this system has been creating a new PCB so that we can actually start testing this. Alrighty, so this summer we were using the EDA or Electronic Design Automation software of Altium, which is a new software for the Engineers for Exploration program. And we essentially had a previous model from the prior Smartfin 2.0, and we had the PCB or printed circuit board and the schematics. However, none of our schematics had a library, which is where it stores the schematic and footprint, which is how we can actually create the PCB. None of that existed. So we essentially had to go all the way in and recreate every single aspect of it. So this right here is the interface for creating components in Altium. So we have the schematic, which allows us to make actually bigger schematics and allows us to see the electronics in it. And then of course we have the corresponding footprint. And these are all on a PCB, little metallic pads that are electrically conductive and correspond with each of these panels. This is an example for an integrated circuit, the little IC, and we basically had to recreate all of them. It's essentially like having a Lego set with no Legos and just the instructions. So we updated all of the circuitry to reflect that of the new system on a module, the TSOM. And this next slide is going to show us the previous E-series. So this is the big overall main document for the last model. As you can see, this is the E-series schematic, but what we did is we created this. So this guy is the TSOM. And all of these different types of peripherals, all of these pinouts had to be completely remapped and rewired, but reflect the same circuitry. So these function essentially the same. We removed the GPS because it's now on the system, and we had to recreate every single one of these components that you see. And so that's what most of our summer on hardware was based around.
Yeah, so then we took that schematic design, put it into Altium, which is a computer-aided design software, and we made it into our PCB. So this is a little snippet of the actual PCB, and on the far side there, you can see before everything is routed, then what a part of this PCB process is taking all of those, they're called air wires, and it pretty much just shows you how things should be connected, and then actually figuring out how to connect them up. So you draw all these crazy lines and use some holes called vias to bring things to different layers of the board so that you're not creating a bunch of shorts as things cross. And then we had our PCB, and before we could get it printed, we wanted to do, and as everyone does with the PCB, a design rule check. So this ensures that you don't have a bunch of errors in your board when you actually get the physical board. It's making sure that things like resistors and different components aren't overlapping or touching the edge of the board.
And so with the PCB editing process, there's a lot of iterations that we need to go through, and that means a lot of paper. We printed out probably an inch or two worth of paper, and I've scribbled all over it. And just throughout the process, there's a lot of really important considerations. And these include amperage, which of course is the amount of current that different types of devices are going to be carrying. This bottom sheet right here is one of our amperage layouts. We highlighted different components that carry 300 milliamps and the ones that carry 30 milliamps. And that just determines the width of the wire. Now, the wider the wire, the more amperage it's going to carry. And then of course, size is a really big deal when you're working with constrained spacing. You need to have this PCB fit into that of a surfboard fence, so it can't be too big. And then of course, component location is also important. When you have things like capacitors or high-speed wires, you need to make sure that everything is in an orderly fashion and able to function correctly. So throughout this iterative process, we used Altium's built-in version control, which enabled me and Jordan to work essentially at the same time on this PCB, which really sped up our process. And throughout this iterative process, we were able to produce, hit the next button, this PCB. So this is the 3D model of our current PCB. It's about, let's say, yay big. And this is the final board that we created for the Smartfin 3.0. As you can see, I was talking about the T-SOM schematic earlier. And if you look at all of those little boxes around there, that is the footprint of that T-SOM. And we have different little guys all around this board that enable us to effectively run our Smartfin.
Yeah, as a result of all these hardware changes over the summer, I've been currently working on developing a new version of the firmware for the T-SOM as part of this transition from the E4 to E4E. This has entailed porting over a lot of the logic from the old firmware, redesigning a lot of the sensor suite firmware with the GPS now being on board, that new redesign, as well as providing a better foundation for future development and future sensor integration. So as part of the sensor, a lot of my focus this summer has been on writing firmware for the sensors, various sensors we're using, from the temperature sensor, the wet dry, the GPS, there's some other carbon sensor, and all of that. Some of them largely stay the same. The temperature sensor and the wet dry sensor were able to be largely reused from the old version, and that made my life a lot easier, but it made some sensor code had to be largely rewritten and redesigned, such as the GPS, which is now being on board the T-SOM compared to the E-series, that had to be rewritten using a different driver and library. Others, such as the accelerometer gyroscope motion sensor system, also was rewritten to provide a better foundation and feature set for future development, such as turning it into a wave sensor in the future. And then as part of this, I've also integrated the systems for data collection and upload. I had to largely rewrite the system for storing data when the Smartfin is out in the water and collecting the data from the various ocean metrics. This had to be largely recreated because the T-series has a different file system in the old E-series, initially I did reset the uploading, where we upload all the data we collect to the cloud for our use for future research. In order to do all of this firmware development, while the electronic circuit board was being developed currently, I developed a test bench for this development. We see on the left a large evaluation board where we have the P-cell in the middle and a bunch of connections out to various sensors. One of these sensor boards on the right, which is for the motion sensor, allows for development of firmware without the need for the still in development circuit board that Josie and Jordan were working on. In terms of software side of this test bench, I've created a command line interface that allows for things like manufacturing testing, which you see here, and making sure that various sensors do actually work. And on the electrical side, it also allows us for data collection, for making sure general health of the system and other debugging aids. And that's been a lot of my focus this summer.
So this summer, I worked in parallel with the electronics team to build the physical fit. So the process for that was designing a mold, which you can see here. Here we have the two sides of the mold with negatives cut out for the fin. So from this is on CAD that it has been sent out for manufacturing. From this, you get to the actual fit by cutting out sheets of fiberglass and laying them into this fin-shaped area, and then fitting the PCB that Jordan and Josie designed into these pin holes, and then laying all other necessary components around them. Then lay more fiberglass, attach these two sides of the mold together, and then pour resin, epoxy resin for these two holes in the top. And the idea is that it will then harden and take it apart, do some post-processing, and then have it up in water. You can see there are a lot of like extraneous components, lots of like little things we had to add for this to work well. Go to the next slide. Here's a drawing of one of those parts. So the first stage of building this mold was designing it. The second stage was working on manufacturing. So what that entailed was making sure that corners weren't too sharp, making sure that things that were less relevant, like fuse gutters, for example, were marked as non-critical, and talking to machinists who gave us advice on how to make this easier to actually build. So this mold has been sent out for manufacturing. It's currently in process, and once it's back and all the components are put together, should be able to get out on the water, which I'm excited to.
Yeah, so like Ela was just saying, our future goal and going into the next quarter is to take the PCB that's currently being printed and take that mold and put our PCB in that mold, get everything ready to be in the water and start testing and getting those range of data points again so that we can get surfers out there with the Smartfin. We're also working on developing new sensors to integrate into the TSOM and the Smartfin. So this summer we worked on starting to figure out how we can integrate a salinity sensor, and that will continue as we move forward. So we would like to thank all of our advisors, Nathan, Brian, and Kurt, and we'll open up the floor for questions now.
Always the question. No, very cool. I'm familiar with Smartfin, but I'm curious what's the purpose or function of the mag on that top here?
Yeah, we're hoping to use that in the future to measure wave height and get the location of the help use that to help measure like wave height alongside other motion sensors and stuff like that.
So is it picking up ferrous material and sand? So it's
Really part of an interval measurement unit. So we're doing.
Okay, I got it. I thought it was like an environmental sensor.
No, the intention is to basically be able to implement like a common filter or something.
Okay, totally understand.
Yeah, so we use those 3 parts of the motion sensor and then kind of like combine them all together to get wave height.
Okay.
But those calculations are like still in the process.
And is there some talk about having, because this is a single fin, right? And obviously it's a standard slot for most surfboards. Can you expand the sensors across the other, say, 2 fins if it's a tri-fin board, or I mean, obviously the form factor of certain sensors can prevent you from getting it into a fin. Like I guess if you were to have a higher sensor or something tricky, but is there talk about expanding across the other 2 fins on a tri-fin board, or?
Yeah, so the main reason we've kept it in 1 fin is because if we're connecting the other sensors, then there would be housing that has to like modify someone's surfboard. And we've found just from previous experience working with surfers that they typically don't want to do that. But our like PCB and components within the fin are small enough right now that we could put it in a smaller fin. Like we have this in a longboard fin, but we could get it to fit in like a shorter board, like a 6-footer.
Yeah, and then also the previous Smartfin models were based off of twin fin design, so the double fin. And basically, like Jordan said, we should be able to put that into any of them, but we are aiming towards the long fin for now, the longboard fin for now, because of just the space and the ability to test the space.
How are you making fold? Is that like milling, printing?
Yeah, so it's being milled, and I'm not actually doing it, we've sent it out for manufacturing. But the previous iteration, there was an image of like version 2 of the fin. They actually 3D printed half of it, laid down the electronics, and then put fiberglass on top. And their fin was like a little flimsier, there were cases where it didn't snap. So we are just milling the whole mold, and then from there.
Okay, great. I think in the interest of time, we should move on. We have 2 more, right? Okay.
All right, yeah, we'll welcome Acoustic Species Identification.
So like Glenn said, we're the Acoustic Species Identification. I'm Sean. I'm joined by my co-project lead Sam, Ben over there, and Marco with us on Zoom today. So today what I want to talk a bit about is biodiversity loss. Across the globe, there has been widespread biodiversity decreases, not the least of which in South America, where there has been a whopping 94% reduction in biodiversity in the area. This is obviously of concern to our collaborators such as San Diego Zoo Wildlife Alliance, who are really interested in being able to more finely understand what species are being affected by factors.
What happened to my sound? Oi, oi, oi.
So to do that, there's a handful of ways of being able to monitor your population. Common method is camera traps. Camera traps have been commonly used for the last few decades, and they're really, really great at picking up these larger animals such as tigers. Plus, images are more research field. You can do a lot of work with images, and it's really easy for citizen scientists in order to label your data. The problem is, large animals don't make up a large amount of the biodiversity. Most of the animals in the world are much smaller, they're harder to see, like birds, insects, bats, etc. So we're missing out on a bit of biodiversity here. But the thing about all these animals is that they're really noisy. So if we can pick up them in microphones, such as audio moths, shown in the right side of the slide, then we can pick up a larger array of animals and hopefully get a lot more data about what species are affected. The difficulty is the scale of the data we collect. To put this into context, the San Diego Zoo Wildlife Alliance collected about 1,500 hours of audio data in 2019. Our previous testing with birders from San Diego, looking at Surf's coastal data, it takes about 3 seconds to label 1 second of audio data. So if we have 1,500 hours of audio data for Peru, we gotta process. That's 4,800 hours of manual labeling or 187 days. That is not sustainable in the long term, and it's probably not even viable to do from the get-go. So we need to have some way of automating this process. So the big question is, how do we go through and use techniques like machine learning to analyze this audio data?
So while we could operate directly on the waveform, there's been a lot of research done in creating machine learning models to do image recognition. So to capitalize on this, we can convert our waveform on the top to the spectrum at the bottom. So we're going to play an example of some of the data that we collected.
Of course it doesn't.
That's all right. Well, so, as you can see, there's some spikes in the waveform, which correspond to generating the signal from a streaming feedlot. They have short calls and then the long version call. So it's a lot easier to interpret when you can see it on the image. So most of our data comes in like this. We have a clip level label that says there are streaming feedlots in this call somewhere, but we don't really know where. If we were to directly train on this data, hopefully the model will vary the calls. There's also going to be the background message there, where it thinks there should be a call, but there actually isn't. So we can pre-process this using binary for detector, such as tweeting it using our Python package PyHop. What this does is it brings our data from they're somewhere in the file to, oh, they're at 2 seconds and 4 to 5 seconds. This should hopefully make it easier for us to figure out what's going on and for the model to learn. We can then pass this data into our multi-species or train a multi-species classifier using this data, which hopefully can distinguish between different bird species by their calls.
So as Sam mentioned, if we take a 1-minute clip and our model takes in 5 seconds of audio at a time. If we take a 1-minute clip and split it into consecutive 5-second chunks, there might be one that has just background noise and the model's not going to learn from that. So this graphic here shows how the performance of PyHop, using PyHop improved our model performance by centering the chunks on where the bird is in the clip. So on the y-axis, we have CMAP, which is a metric that calculates accuracy. It's essentially like accuracy. And then on the x-axis, that's how far we are through the training process. As you can see, raw chunking, which is traditionally used in this context, does not perform as well as PyHop. However, that doesn't mean it performs well on the soundscapes we actually want to run the model on. So here we are testing the performance of the model on 21 hours of a Peruvian soundscape that's labeled by experts. And you can see it's leveling off at about 0.2 on a performance metric, compared to our training data set, which is leveling off at about 0.6. So why are these so different? It's because our training data set and our testing data set are very different. So our training data set comes from Sino Canto, which is someone goes out into the jungle, holds a microphone up to a bird, and records it for about a minute, and then uploads it online with a label. Our testing data set, however, is a soundscape, which is just a microphone put into a bush. And it's much harder to get the data from this soundscape because it has more background noise, because it's not right next to the bird. The birds are farther away. There are more birds in the call in general, and there's sound from all directions. So I'm going to pass it over to our voice in the sky, Marco, to explain how we're going to tackle this problem.
Luckily, we have a few tricks up our sleeve to address this issue. One such technique is data augmentation. This involves randomly modifying training data so that our model is unable to just memorize it all and is instead forced to learn more general patterns that we hope will transfer better to the testing data. Another technique we've been working on is pre-processing. This involves taking the training and the testing data and making them more similar before we ever feed them to the model. A very simple example that we've done is adding a low-pass filter, which simulates the effects of birds being further away in the testing data set, since high frequencies fall off more quickly with distance. Another technique we've been using is pseudo-labeling. This involves taking an unlabeled data set, running model predictions over it, and then taking the most confident of these predictions and adding them to the testing data set. The idea behind this is that the most confident predictions will usually be correct, and so we want to reinforce them. Overall, this still remains an open research area, but we expect that these three techniques, as well as other techniques may discover, can help us make significant progress on this challenge.
At this moment, I would like to thank my team for their hard work. This presentation does not show some of the hundreds of runs that we've done with our models to try to add incremental improvements each time. They've been a big help this summer, and I want to give a big thank you to them. Also, a thank you from our San Diego Zoo collaborators, Anias. Without their support for about the last 3 years, this project would not have been possible, and they have been very, very helpful in keeping with us. And of course, from our team at E4E, Nathan, Kurt, and Brian, they have all been very, very helpful, meeting pretty much weekly with us, keeping this project going. So, big thank you to them. At this moment, I would like to open up the floor to any questions you may have about the project. Sure. So for the audience, someone from E4E is going to play the peacock that we were trying to play earlier. It makes a really fun noise. Second loudest bird in the Amazon, or actually in the world, and it's just a funny bird.
So this is the clip from the San Diego Zoo. They have a screen peacock in their
Hummingbird.
yes.
Go in the morning, they're the most active during the dawn and dusk.
So they are quite. This video does not do it justice on how loud this thing is.
For context, you could be about 100 feet away from the hummingbird exhibit, and you will still hear the screaming peacock. They are very.
The data augmentation approach, where you're introducing any kind of specific acoustic signal that is not relevant. How does that work? Like how does the augmentation part of this work?
So there's a handful of different techniques that you can use for data augmentation. For instance, you can introduce additional background noise. So we have recordings that just have no bird calls in them that we can introduce and mix in, basically just adding the two signals together with some alpha range. So you have alpha and then 1 minus alpha, so you can combine them. They're still the same magnitude, but you have a new signal. If we do that over and over again with different combinations of background noise, then the model isn't just simply overfitting onto specific background calls. There was a funny point where, so for machine learning, you have to do a train test split in order to validate if that results work. We once did a train test split just on the chunks themselves, so of the individual 5-second calls, and we found that the model actually reported higher validation results than it should have. Partly because it memorized the background noise of where the file came from, where the bird was. So if you have the same file, the same bird's probably in that file. So if you have the bird in training and you have the other clip in validation, of course it's going to do better. It's just going to memorize the background. So those kind of data augmentations can help the model stop memorizing that and focus more on the more important signal we care about, which is the background, which is not the background noise, the bird. In addition, we have also many other techniques. We can mix in other bird calls and then tell the model to try to predict both birds. We can mix in just ordinary white noise, pink noise, brown noise. There's a lot of different techniques that we can do to play around with the audio a bit, but still have the same signal in there in order for the model to generalize a little better.
Do you have a mix of different training sets? So they all like Xeno Canto is the one that's very clean, or do you have like some that are also like expert labeled soundscapes where they sat around like a long recording and tried to identify everything?
you got this.
Yeah, so our main, it's actually no problem trying to shift Xenocanto to soundscapes. So we're trying to use Xenocanto data for soundscapes, or Xenocanto data for training. And there's a number of soundscapes released from like bird club competitions, which are competitions specifically focused on solving this problem. So we have about 7 or so expertly labeled data sets from different regions. And we're just using them for validation tests here. Because if you wanted to deploy this in the field where it didn't have that label, ideally you still want to use this.
The key problem here is we don't have enough human labeled sensors. Because we mentioned we had 21 hours, those are 21 files of 1 hour soundscapes. And for the same reason I mentioned earlier with the training test split, if I were to take a sample, I would have to take the whole file and give it to the model. Otherwise, it would just memorize the background noise and report higher metrics than it realistically do. So when you start taking chunks out of the files, that reduces the amount of testing data we have. And that starts messing around with your bias variance trade-offs when you get into when you start reducing the size of your test set, and so on. The best thing we can try to do, there's an approach that we're currently working on experimenting with pre-training the model. So the idea is we have it train on a much larger range of data and then fine-tune it in the later stages of training on the birds we care about. That way we could potentially take advantage of soundscapes from other regions of the world and then fine-tune on Xenocanto. Still untested, working on that right now.
So your training data set has both unlabeled and labeled data?
So it has labeled data, but as we talked about, so the process of the data set is it's weakly linked. So from Xenocanto, we know that the string plot is somewhere in the clip. What we have kind of done is that we have really good binary bird no bird detectors that we've spent the years of 2020 to 2022 experimenting and testing on. So when we detect a bird, we're really confident there's a bird in that region we detected. So the idea is we can convert this to what we call strongly labeled data to make it much more clear to the model where the bird is in the clip by applying these bird no birds on. So to answer your question, technically it's automatically labeled, strongly labeled data. So we do have it.
And we should move on. One more, right?
Yeah, we do have one more.
And people will stick around and get more questions. Please, please feel free to keep your questions for later.
At this point, I'll pass it off to the Mangrove Monitoring team.
So hi, my name is Jason. I'm one of the project leads for the Mangrove Monitoring project of Michael. And so to start off with, so like what are mangroves in the first place? So these are these like big wetland trees that grow in like swamp areas. If you're familiar with like the Everglades in Florida, that's one place where they exist. They also exist in like the Caribbean and other similar swamp-like places. So why do we care about these trees in the first place? So these trees are big for climate change. They take carbon out of the atmosphere and they store them within themselves. So there's one statistic that they store up to 5 times more carbon than your typical like on land forest. And this is a huge impact for global warming and climate change today. Another big benefit is that you can see there's a lot of fishing that goes on in these areas. So they provide habitats for fishing, but they also provide economic benefits for those local communities that rely on fishing for their economy. And they're also a good natural storm break. So any hurricanes in the area, these do a good job at slowing them down. So because these forests are so important, we want to help support these researchers who are kind of researching these areas. So what we do is that we take in drone and satellite imagery on the left over there. So you can upload any drone or satellite image that you might have. And then we'll do some machine learning stuff and then we'll classify it for you. So what you see on the right are classifications that we did on this drone and satellite image. So anything within these blue boxes are places where mangroves exist. And anything outside those blue boxes are where mangroves don't exist. So taking a deeper dive into how this website works. So you have the user at the top, and this user kind of just uploads the images. They upload the satellite and drone image, And then we have our static files, which are just for HTML, CSS, or JavaScript, kind of your basic website stuff. And then we also have a web server, which basically controls everything else. So this web server is then connected to a database. So you need some way to store all of the images that you upload, but also store any classifications that you might have already classified. And then we also have this image processing service, which prepares the image for any machine learning models which live in our classification service. So I'm going to pass it off to Michael to talk more about the machine learning models that we use that are housed in this classification service. Oh, and we also have a reverse proxy to add some extra security onto everything.
So on the machine learning side, Mangrove Watch, which is an organization that tracks mangroves globally and compiles mangrove statistics, how they track mangroves was they took satellite imagery and then they broke it up into individual tiles, 120 by 120 pixel tiles, which is about 400 meters by 400 meters. And then they would run a classical machine learning algorithm on these tiles to classify them as mangrove or no mangrove. And prior to the summer, we improved upon that by integrating drone imagery into this to improve the accuracy of this classification. However, there's a couple problems with this. The first one is that our machine learning model required the drone imagery to achieve higher accuracy. And on top of that, so we wouldn't be able to look back historically at the mangrove loss over the years because we only have drone imagery from 2022. And then on top of that, the accuracy wasn't great because we'd be classifying a whole 400 meter by 400 meter tile as mangrove or no mangrove, even if that tile had 60% mangrove coverage or 70 or 80 or so coverage. And so the goal for the summer was to take just the satellite imagery of this area of Jamaica that we wanted to study, and then apply state-of-the-art machine learning techniques such as semantic segmentation in order to get a more fine-grained classification that didn't just classify each tile. And so semantic segmentation is used in autonomous vehicles, for example, to detect objects and people and other cars. And how it works is it takes an image down to its latent space representation, and then it decodes it into a per pixel classification. And so we tested different semantic segmentation models this summer. The blue data points represent the accuracy of previous models that we had prior to the summer. And then we tested the DynaV2 class with a unit backbone up there in the purple. And then we also tested the segformer class of semantic segmentation models. And we didn't just care about the accuracy, we also cared about how big these models were because bigger models are more computationally expensive and also slower to run. And so the size of the data points is how big the models are measured in parameters. And so our DynaV2 model was both inaccurate and it was super big with 300 million parameters. But we found that our segformer MITV0 had a good trade-off between accuracy and model size. And if we wanted the best accuracy, then we'd go with our biggest segformer model, the MITV5. But this chart doesn't fully represent how much our models improve accuracy-wise over the previous ones, just due to the fact that a lot of the satellite imagery is no mangrove, so it'd be super skewed towards correct classification. And so here's a visualization of these results. So in the top left, you can see satellite imagery of 3 bands of the satellite. And then the bottom left is the true ground truth labels that we labeled using our high resolution drone imagery that we collected. And then the top right is how Mangrove Watch and our previous models would classify this tile, which is completely mangrove, just 100% mangrove coverage. But then this is our segformer MIT5 model and how that stacked up. clearly like has better per pixel classification compared to our previous models and the Mangrove models. And it's quite similar to the drone ground truth maps. And currently, we're also developing a pipeline that pulls satellite imagery, then processes it, and then given an area, tracks the mangrove loss of that area over the past decade.
And to finish off, we're currently working on a research paper that will hopefully be submitted by late September. And it's kind of going to go over all of the various machine learning techniques we've used. And to finish this whole thing off, we'd like to thank our collaborators. We'd like to shout out Nathan, Chris for helping us on the website, and also the professors too. Really everything has kind of all the support that we've received to make this project kind of come to life. So with that, I'm going to open the floor to any questions that anyone might have.
My main comment is you should be an optimist, and maybe at some of those points, mangroves will start growing back. Any other quick questions? Okay, thank you. A bit longer than we expected, but there's a lot of really great work that we did this summer. So congratulations again to everybody who's participated. Certainly this will all be used a lot in the future. Very exciting things happen, I think, in all of these projects. So again, thanks a lot for helping move all these projects along. Many of them are many years old, and you're kind of remembering and heard, and you have definitely pushed them along in a really nice way. Keep in touch. All of you, please do keep in touch, and here are our mechanics. Or just send an email. And some of my favorite emails are, hey, I got into grad school, or hey, I'm working in this company now, and doing this kind of stuff. So please keep in contact with us all. Thanks to everybody who's still online. I didn't get to see who was there, but thanks for sticking with us. And yeah, congrats on finishing.